So besides the properties that I talked about in the last video, so the sum and difference, product quotient, and then composite function properties that we use for limits, we need to talk about a couple of different kinds of functions that we're going to see in calculus. So with limits now and then with other problems later, and one of those is absolute value functions. So we need to be able to see a function like this and know how to deal with that in terms of limits. And then being able to do this with limits is going to allow us to do things with our more advanced problems because those are going to be based on limits. So if we have a function that's defined as an absolute value function like this, and we want to take a limit as x approaches any value, I'm going to say 1 here of f of x, we need to know how to handle that. Now, this particular absolute value function is a relatively simple one. So we could probably evaluate this limit informally by just understanding what the graph looks like. And that's where I want to start with this. So remember, with an absolute value function, essentially what we do is we take the inside function, the x squared minus 1, and anywhere that's negative, it becomes a positive. So this function is going to be exactly the same anywhere the function is positive. So here and here. But then where the function is below the x-axis, we get negative values, and an absolute value is gonna flip that. So anywhere we get a negative value, say here at 0, -1, becomes a 0, +1. So all this stuff below the x-axis is going to flip over, and it's going to look like that. So an absolute value function, we get bouncing happening anywhere the function is going through the x-axis. And then the absolute value part of it is going to be always positive, so always above the x-axis. We could have some changes to this. So if we took this absolute value function and subtracted 2, then our x-axis would be here instead of where it is. So it is possible for a function with absolute values in it to be below the x-axis, but the absolute value part itself is always going to be positive. So how do we handle that analytically? Okay, this is a graphical approach here, but we need to know how to handle it analytically also. And what we're going to do is the same idea as what we talked about with the graph, but we're going to do it algebraically. So we're going to say, okay, the function's the same if that part's positive, and it's going to be the opposite if it's negative. And the way we handle that is with what we call a piecewise function. So we're going to say this is equal to, and we're going to have a couple of branches here. So it's going to be the same when the inside part is positive. So if x squared minus 1 is positive, then it looks like that. If that is equal to 0, which happens at -1 and +1, then it actually doesn't matter which branch we put it on. So I'm going to put it on the positive branch. So if x squared minus 1 is greater than or equal to 0, then the function stays the same. There's no change to it. However, when x squared minus 1 is negative, then the value of the function is the opposite of what it is. So I'm just going to write it like this. So I'll put the function in parentheses, put the negative out front, and that's what's going to effectively flip it over the x-axis and make it positive. All right, and we know this is the case because when this is negative, if we take the opposite, it just makes it the positive value. And then we can do some simplifying here. This is an inequality that you can solve in a few different ways. One way to do this is to just solve the equation x squared minus 1 equals 0, get solutions, check regions. I'm not going to go through all of that here, but this function is going to end up being x squared minus 1. Actually, I'm going to make this a little bigger here, because what's going to happen is we end up with 3 branches, because this is when x is less than or equal to -1, or x is greater than or equal to +1. So I'm going to write this actually as 2 separate branches also. So it's equal to x squared minus 1 when x is less than or equal to -1. This is going to be when -1 is less than x is less than 1. So it's going to be negative x squared plus 1 on that region. And generally, when we're writing piecewise functions, we like to go in order with x values. So the first x values starting on the left are these here, and then moving down. So back to the original function for values of x greater than or equal to +1. So what we've done is we've basically just said, okay, we can look at different parts of the function depending on the x values that we're dealing with, and then evaluate limits from there. Now, we got to know how to handle limits for a function that is a piecewise function. So the example that I gave, the limit as x approaches 1 of f of x, is actually going to use two different branches here. So remember, with a two-sided limit, so as x approaches 1, it has to approach the same thing from both sides. So as we approach x values, as we approach 1 on the x-axis, but values that are smaller than 1, has to match what we get when x values are slightly bigger than 1. So I'm going to go off to the side here, and I know I'm kind of all over the place on the screen here. So if we're approaching 1 from the left, then we need to know which branch to look at. So looking at this function right here, we're approaching 1 from the left. So numbers really close to 1, but slightly smaller than 1 is going to be this part right here. So this is the same thing then as saying the limit as x approaches 1 from the left of negative x squared plus 1. And there we can just plug the 1 in. Remember, this is not a negative 1. It's 1, positive 1, but just values slightly smaller than positive 1. So we plug 1 in and we get 0. Now, if we're doing the right-handed limit, so the limit as x approaches 1 from the right side, now we're looking at values that are slightly bigger than 1, so we're going to be on this branch right here. So that's going to be the limit as x approaches 1 from the right of x squared minus 1. And we plug the 1 in there. Direct substitution works because we get a number. That number is 0. We have the same limit on both sides. So that means that our two-sided limit over here exists, and it is 0.